Tamam, başlayalım. Ders başladı millet. Uyandırın şunu yani, ders başladı. Sen bu dersi mi alıyorsun? Uyan öyleyse. So last time, this is where we left off. Şu arkadakiler ön tarafa gelebilir mi? Arkaya gitmeyin. Ön tarafta, ön safları sıklaştık. Arkada durmayın. Size söylüyorum, ön tarafa gelin. Emrah çekiyor mu maçı?
Çekiyor hocam şu an.
Akşam fırtınalar çıksam yılın geldiğini görsün. So last time we did this. We talked about interprocess communication, and we said that these two processes or two threads need to share some data, use the same memory location. They need to be careful because there might be some race conditions, right? There must be some race conditions. We talked about those, and to prevent the race conditions, we use this technique, mutual exclusion. So, mutual exclusion meant that if some memory location is shared by more than one processor or one thread, then that region has to be used in an exclusion, in mutual exclusion. That means that only one of them can use it at the same time. And to do that, we say that the processes can access that mutually exclusive areas only in the critical regions. Okay, so this is what we talked about, and for the critical region we had these rules. We said that no two processes can be simultaneously inside the critical region. This was the most important, but there were some other rules too. So I will not go over them. You already know them, and we said that one of the most primitive ways of achieving this is that, achieving the number one requirement, no two processes may be simultaneously inside the critical region, is the busy waiting. Busy waiting meant that if a process is inside the critical region, the other processes needs to wait for this process to finish its job. So they keep running this infinite loop until the other process finishes its job in the critical region. So one of the ways of doing this mutual exclusion was disabling interrupts. So disabling interrupts was when you disable the interrupt when you are in a critical region, our purpose was to prevent any interruptions, any interruptions of the process, so that inside the critical region the process runs until it is done with the critical region. But this didn't work all the time. What was the main problem with the disabling interrupts?
It doesn't work on the multi-core.
Yes, it doesn't work with multiple CPUs, because if a process is running on a CPU, another process is running on another CPU, they are running simultaneously. So there are no switching back and forth between these two processes. So multiple disabling interrupts is a good solution for multi-core, multi-processor systems, which is getting more and more popular. Even the cell phones are multi-core machines. So this doesn't work. Another thing is that available only to the kernel, so at the user space I can't do that kind of stuff. So we skipped on this, and we talked about this lock variables. So we say that when we are getting into the critical region, we try to lock a variable. We say that if the variable value is 0, then it is okay to go into the region. Then even if I make this lock guess the value 1, and I increment by my value like that, okay, and I make it lock 0 so that other processes can go in. What was the problem with this one? There was a problem with this one.
There can be process switch.
There can be a process switch where? There can be a process switch right here, right? Two processes, A and B, start running. Okay, they are running. A is here. A look at the value of lock, and it sees that it is 0, and A come here. It comes here. It's A here, and process switch to operating system switch the control to B, and B came there without A making any changes. B sees that lock is 0. So both of them can enter into the same critical region, which violates the rule number 1, right? So this is not a good solution. The problem here is that you cannot prevent two processes. You cannot assume anything about when the processes are going to be switched. Okay, so it can happen anytime, and this is a computer world. You know that even it's a very, very small possibility that switch is going to happen here, it will happen someday. And if it once happens, it crashes. I mean, it is enough to crash your computer once a day to make it a bad operating system, right? If your cell phone crashes once a day, single a day, that means that you lost 50% of your customers, because iOS doesn't crash once a day, it crashes once a week. I don't know. So even if it's a very small 1 in a million possibility, it will happen, and it's a bad thing. These kind of things should not happen. Yes.
Atomic fonksiyonlar.
We didn't talk about that yet. So that's one of the solutions. Okay. So let's move on. Some people say that C++ is C or very clever. Let's do this. See what does this do? It takes the value of lock, right? And if it is not 0, then it quits the. Understand this? It tries to increment the value of lock, and if the initial value of lock is 0, then it quits the loop and it enters the critical region. But if the value of lock is not 0, then it decrements it and it keeps doing the same thing. So it is trying to do it in a single instruction, right? I mean, but just a single statement like that. It has the same effect of this. Yeah. Check the lock value. If it is 0, then quit the loop and make the lock value 1. And it is doing the same thing. Okay, it is doing the same thing. So they are trying to do this so that there is no context switch while I am executing this statement. There is no context switch while I am executing this statement. That's what it's trying to do. But it's a very simple C statement. But when you translate it to the assembly language, okay, it is not that simple. Okay, it's like that. So load the lock variable into register 0, copy register 0 to register 1, and increment register 1 by 1, and store the new value to the lock, and check if register 0 is 0, and then enter the critical region. So that simple line of code, 2 lines of code, is translated here. So when you read the lock variable to register 0 here, and the context switch happens here, then you have the same problem. So your C statement simple doesn't mean that it will be a simple assembly language or machine code translation. Okay, so no solution here. So we don't have any atomic increment instruction in most of the CPUs. You need to load them to a register, then increment the register and store it back. Okay, at these 3 steps. And if the interrupt happens while you are doing these 3 steps, then you will run into this race condition. Okay. Question on this one? So this is not a good solution. We need to come up with some other solutions. What did we say? We are going to use lock variables and we are going to use strict alternation. One solution is to use strict alternation. It says that, okay, I have 2 processes, A and B. Okay. Let's use the critical region in turns. First, A will use it. Okay, turn number A. Then B will use it. Then A will use it. Then like that. Okay. So they will take turns. Once A will use the critical region, then B, then A, then B. It goes like that. Then it's called strict alternation. Okay. So I have 2 processes here running this loop. Okay. It is almost the same, only the process numbers are different, okay? Only the process numbers are different. See, there is an infinite loop, infinite loop. It says that if this is process number 0, and this is process number 1. If the variable turn is not 0, okay? If the variable turn is not 0, then infinite loop. Okay? If the variable turn is not 0, then do this in an infinite way. That means that it's not my turn. So it's doing a busy wait here. Busy wait here. Busy wait is something bad because it wastes the CPU time, but for now we are going to do it. Okay? If the turn is 0, then it enters the critical region. It finishes up its job with the critical region. It makes that, okay, it's now your turn now. Okay? It's now your turn. And it does the non-critical region. And it comes back and looks at the turn again. If this is the only process running, then for the second iteration of the upper loop, this loop, it will not go into the critical region because the turn is now 1, right? It has to wait. It has to wait for what? It has to wait for this process to make the turn 0. Okay? So only one of them definitely inside the critical region. No two of them can be inside the critical region. Okay? But they have to switch in alternation. Yes?
Hocam üçüncü bir tane daha olsaydı o zaman ikisinden hangisini seçeceğiz, nasıl yapacağız?
Nasıl bir tane daha olsaydı?
Bir tane while yani proses oluyor, bir tane daha proses olsaydı.
Third process, number 2. No, well, it doesn't work that way. I mean, in that case, your solution, I mean, maybe that's a good exam question. I will not answer that. You think about it, okay? So the question is, if we have another process, how would this work? And the solution would be, I mean, wait this ABC and 1, 2, 3, okay, 4, 5, 6, go that way. So I mean, you could develop your own solutions, of course. But the problem is not here. If we have more than 2 processes, the problem is here. What is the problem? What is the problem? There is a very serious problem here.
Bilgisayarlarla çalışma var aslında.
Huh?
Hani they don't work at the same time.
They are not supposed to
Wait
work at the same time.
Wait
What?
for each other.
That's the idea of critical region. I mean, only one of them can be inside the critical region. That's what we are trying to do. That's what we are trying to do. Remember this picture? Only one of them are inside the critical region. Okay? No 2 processes can be at the same critical region at the same time. Okay? So if you have the turn, if you have the token, then you are in your critical region. Otherwise, you have to wait. Busy wait.
Yes, actually doing busy wait. No.
So it's a busy wait problem. Busy wait is a bad thing, I know. Yeah.
No.
But I mean, it's not a problem for this mutual exchange with busy waiting. There is another problem. I mean, I am not talking about the busy waiting problem. We will come to that later. By the way, busy waiting is not a very big problem. I mean, we can solve it, or sometimes we don't have to solve it. Sometimes we like it.
The problem is, I think, one process may have to leave its critical region right before its job is done, right?
One process may have to leave the critical region before its job done. Well, I mean, once you are in your critical region, the control is yours. You don't have to yield the control. Actually, I mean, you can do whatever you want inside this. I mean, while you are inside this critical region, the other process cannot be inside the critical region. Are there any race conditions? No. I mean, when I read that value turn, if it is not 0, then I'm gonna loop. And at the same time, if the other process makes it 0 when I read it, then that's okay. In the next file loop, in the next loop iteration, I will quit the loop. That's okay. I mean, making this turn 0 at the same time while it is reading it, it doesn't cause any problems. Or while this one is waiting, the turn to be 1. If it at the same time, if this one makes it 1, then that's okay. And then at most I will make one more loop iteration. There are no race conditions. The problem is this. The problem is this. If process 0 is running too fast, okay, let's say it is running like 100 times per second. This one is running maybe just once a second, okay? This is running very, very fast. This is a very slow one. So that one has to wait for this one to come to the critical region and do its job. And I mean, this non-critical region might be very computationally very expensive, this region, okay? So this process, while it can continue, it has to wait for that process to come there, get into the critical region, and to make it turn 0, okay? So that violates one of our rules. What is the rule number 3? No process running outside its critical region may block the other process. Okay? This is what happens. I am here, okay? I am running very, very fast. I completed one iteration and I made it to turn 1. When I come back here, the turn is 1. I cannot go into the critical region. This one is waiting inside the non-critical region to finish its job. So I am waiting for the other process to finish its non-critical region. So I am waiting for nothing, right? Even though I can get into the critical region, I have to wait for this process to finish its job. Okay? So that's the problem with the mutual exclusion, strict alternation problem. Okay? So it solves the race conditions mutual exclusion problem, but it causes very serious performance issues. Okay? One is dependent on the other. Questions? You see the problem, right? Okay, I will continue then. So strict alternation problem is process 1's non-critical region code takes a long time to execute, and it will enter its critical region until that process 0 can't enter its own critical region. This is very different from waiting for other process to leave its critical region, right? I mean, this one is not waiting for the other processes critical region to be done. This one is waiting for the other process non-critical region to be done, which is a very serious problem. Okay, then continue. Efficiency problem is efficiency principle is violated. Then we continue with another solution. It is Patterson's solutions. Okay, it doesn't use any strict alternation terms. Okay, as soon as the critical region is available, nobody is in there. You enter the critical region, and it doesn't have any race condition issues as the lock variable method. This is the code, very simple code. This is the enter region. Okay, you run this. You call this function when you are entering your region. Okay. If the region is available, then it immediately returns back and you continue with your work. And when you are leaving your critical region, you call this function. Okay, two functions. When you call this one, you enter your critical region. When you call this one, you are leaving your critical region. If the critical region is not available, this function will not return immediately. It will wait inside this while loop. There is a while loop. And see this one, it's an infinite loop until these conditions are met. Okay. So there is a semicolon there. So let's look at it. So we have some defines. N is number to a number of processes. You could have many processes, more than two. Make that n 5, 10 or whatever. And again, there is a turn variable, and there is an interested array. Okay, there is an array. Previously we had only turn. See, there was a global integer turn, and what is the initial value of turn? 0. 0 or 1 doesn't matter. If it is 0, then this will go first. If it is 1, this will go first. Okay. So there is an integer turn. It will say whose turn it is, and there is an interested array. Okay, interested array is, okay, the size of the array is 2, in this case, interested. If a process is interested in entering the critical region, then it makes its own interested integer non-zero, otherwise it is 0. Okay, let's look at this one. Enter region. Says that there is a local variable. Okay, so there is a local variable. So there is one local variable other for each process, right? Because it's a local variable. But these two are globals. Okay, these two are globals. And I just calculate the other. You understand this, right? Other 1 minus process. Okay. Other is 1 minus process. So if process is 0, other becomes 1. If the process is 1, other becomes 0. And it says that I am interested in getting into the critical region. Okay, it makes its number true. Then turn is now processed, and this is our loop. Possibly, this is our busy waiting loop. It says that while turn is same as process. I already made it, right? While turn is process, and interested other is true, then I have to wait. Okay. If interested other is true, then I have to wait. If the interested other is not true, then I just quit from this loop and I immediately enter my critical region. And when I am leaving my critical region, I mark that array in my position interested process also. Okay, this is the whole thing. This is the whole thing, and let's see how it works. Okay, so two processes are beginning at from the beginning. Two processes are working, and process number 0 started